Alright, here is another problem. This corresponds to Halliday, Resnick, and Walker, Chapter 21, number 13. I'll give you a moment to read it. Okay, so if you did this problem and you understood how to do it, your final answer comes out to be the following. The charge should be placed around here. I'll call that Q3, and the location of Q3 is at x equals negative 0.136 meters, y equals 0. So that's the final answer. Now if you didn't get that, then I will talk about the entire solution in detail. Okay, so here I go. Alright, so you have to use a little bit of intuition here. So here's the problem again. This is number 1. Write down this is 1 microcoulomb. This is charge 2. It's minus 3 microcoulombs. And you're asked to place a charge Q3 someplace so that the force on it is 0. So you have to consider multiple places. So first look at Q3. Let's say it's positive. If you put Q3 right over here, it's going to experience an attractive force from the number 2, and it's going to experience a repulsive force from number 1. But the thing is, number 2 is a lot closer. It's also the bigger charge in magnitude, so the force from number 2 will dominate over the force from number 1. So there's no way that the two forces can balance out. Now you can try putting Q3 in between. Q3 is positive, let's say. And what happens is it's going to experience an attractive force towards 2 and a repulsive force, again, in the 2 directions. So there's no way that these two vectors, which are pointing in the same direction, will add up to 0. Now you try Q3 over here, and what's happening is it's going to experience a force to the left from the first charge, I'll call that F1, and a force to the right from the second charge, I'll call that F2. Now the force due to number 2 is, even though it's a larger charge, is farther away. So force from number 2 can be comparable in size to the force from number 1. So the only place where you could place Q3 is over here on the negative x-axis. Now you might also ask, can Q3 be placed on the y-axis? So if you test it out here, what's happening is that Q3 experiences a repulsive force, so it's up from number 1, and then an attractive force from number 2, and you've got vectors pointing in 2 different directions which cannot sum up to 0. So the only place Q3 can be located is over here on this side of the axis. Now what you should do is just put some convenient numbers in. So for example, I want to find the distance between Q3 and the origin. So there's my D. Just define a letter, and D is implicitly greater than 0. It's a distance away from the origin. And then draw your free body diagram. So here's your Q3. It's got a force to the left from number 1, and then you're looking for a force to the right from number 2 that's equal in magnitude. And you can start off with Q3 greater than 0. It doesn't really matter. So at the moment, just call it Q3. And then let's write the magnitudes of these forces. So you use Coulomb's law. So the magnitude of F1 is going to equal K Q1, which is 1 microcoulomb, Q3 over the distance between them squared. And F2 is going to equal K minus 3 microcoulombs, but you're going to take the magnitude of that, Q3 over the distance between them squared. Now in the problem you were given that the distance between them was 0.1 meters. So in the denominator you're going to write 0.1 plus D, and don't forget to square it. Alright, now looking at the free body free body diagram, what you're seeing is that if you want the total force to be 0, then the magnitude of F1 has to equal the magnitude of F2. So you take the quantities you just wrote and write an equation like this. So that's going to come out to be a positive 3 microcoulombs. And you'll get that. Let me get a new piece of paper here so that I can continue on this. So I'll move this up. No, I have paper on here. Okay. All right, now what you want to do is simplify this equation. So clearly the K's cancel each other, the Q3's cancel each other, the microcoulombs cancel each other, and simplifying you get 1 over d squared equals 3 over 0.1 plus d quantity squared. And then you have to just solve this, so I'm going to cross multiply, so you're going to get 0.1 plus d squared equals 3d squared. Expand the right hand side, or expand the left hand side. And then I'm just going to, I can see it's a quadratic, so I'm going to just simplify this. Okay, and then you can solve for d using the quadratic formula, so it's negative b plus minus the square root of b squared minus 4ac all over 2a. And then you stick the quantity under the square root into your calculator. And now I will get a new piece of paper. And when you stick it into your calculator, you get d equals 0.2 plus minus 0.346 over 4. And there are two solutions here. So if I look at the plus, I will get 0.546 over 4, which is 0.136 meters. Or I will get a negative number. Now, you have to look at the original definition of d. So back up here, if you look at it, we defined d to be a positive number. It was a distance. And so the sensible solution here is 0.136 meters. Okay, and then you have to, the question asks you where on the x-axis is Q3 located. So you look at that picture, and now you say that Q3 is located at x equals minus 0.136 meters, y equals 0. So that's it.